Okay, let's talk about conservation of energy now with friction. So now I want to talk about conservation of E with friction. So let's add that into the mix and add that to our bag of tricks. Now, key thing to understand is friction is going to cause you to lose energy, at least lose mechanical energy. And what it's really going to do is it's going to turn it into heat, light, sound, something else. Friction creates that. Now I'm going to go back to my basic work energy theorem, and I'm going to say work is equal to change in energy. And that's probably one of the most useful things we can do out of that. In other words, if I lose energy, it's going to be done by work. And it's usually work that's being done by friction. Well, the work done by friction would equal the force of friction times the displacement. So that's going to equal the change in energy. So let's look at a couple examples of it. One, and probably the most common type, would be something like brakes. If you apply your brakes. So let's say we have a mass of 1,000 kilograms and we have a velocity initially of 5 meters per second. So that's how fast our car is moving. And then I'm going to stop the car. And I'm going to stop the car, and when I stop the car, delta x is going to be, let's go 200 meters. So just a nice leisurely stop. That is not a very fast stop. So I'm essentially going to almost let it coast to a stop. And over here, b is going to equal 0. So if I draw a little picture of what's going on, I have a car right there. That's my initial. I have kinetic energy initial, and that's some value. I haven't solved it yet. But over here I have the K final is equal to 0 because the speed is 0. So I've got in the middle, friction is going to do work to stop me. So what I'm going to do now is I'm going to say the work done by friction is equal to the change in kinetic energy. I can put any type of energy in there, but we're talking about movement in the x direction. Kinetic's what makes sense. There is no change in the potential energy. I'm not going up or down a hill. So now what I'm going to do is say the force of friction times delta x is equal to K final minus K initial. As always, that's your basic physics statement right there. Now it's down to solving it. This term disappears, so let's get rid of that. I'm going to get 0 minus 1/2 1,000 kilograms times 5 meters per second squared. So I'm going to get the force of friction times delta x is equal to negative 12,500 joules, if my math is right. But what I wanted to know is the force of friction. So that's my unknown. So divide both sides by delta x. I get the force of friction is equal to negative 12,500 joules divided by the 200 meters it took to stop. That cancels out, 125 over 2, negative 62.5 newtons. Now, the key thing to understand is it's negative because it's causing you to decelerate. You have a negative acceleration, so that makes sense. Now, here's the case where you can go a step further with that. We know that the force of friction is equal to mu times the normal force. Friction is fun. So therefore I can go a little bit farther with this. The force of friction we know is negative 62.5 newtons is equal to mu. So I want to find mu now. Times the normal force. Well, that's going to be 1,000 kilograms times 10, or 9.8. And that allows you to solve it. You're going to get mu is equal to, here's where I don't really have to worry about that really is only indicating direction. So I could make it an absolute value of that. I'm going to get mu is equal to 0.00625. That's fairly low, but again, you took 200 meters to stop. If you slam on the brakes, it's going to be higher than that. Now, let's look at a similar type of problem, and let's see, let's go as complicated as I can get. Let's go with a roller coaster. Because this is a place, and there is somebody that does these calculations for roller coasters. So I got something that looks like that. This is going to be point A, is at the top. Now I'm going to give it some speed. You've got to get over the top of the hill. So I'm going to say I've got a v of 1 meter per second. Let's make the hill, how about 60 meters tall? Now this distance is important, because what I'm going to do now is I'm going to have friction acting along this distance. And I'm going to tell you the distance along the track is 150 meters. So in other words, that's how far friction acts on. And I'm going to tell you the average force of friction is equal to, let's go with 10 newtons. Now I'll just make up a number. Now, and what I want to know is the speed at this point. We'll call this point B. I want to know the speed at point B. That's my unknown. So now, I'm going to start, as I start with all equations, all energy types of things, I'm simply going to say the energy at point A is equal to the energy at point B. And if it's frictionless, I stop there. Now, this is not frictionless. Friction is going to take away energy. So EA has to be the biggest one. So EA minus the work done by friction. It's again minus because it's costing us energy. It's like a tax in your paycheck. It's costing you something. That's equal to the energy at B. That's kind of your physics statement there. Now let's expand that a little bit. At A, I have kinetic energy because I am moving. I also have potential energy because I'm up in the air. I'm going to lose work done by friction as I slide down the ramp. At the bottom, I'm going to have kinetic at B, and I'm going to write potential at B, but this term goes to 0 because I'm going to call that 0. So now, I've got 4 terms, but when we start plugging into those terms, we're going to find out that we only have one unknown. Now, I do have to give you a mass of the cart. Let's say the cart has a mass of 100 kilograms. It's just a kind of a small playground or carnival style roller coaster. So I'm going to have 1/2 mv squared, 1,000 kilograms, times 1 meter per second squared, plus mgh, which is going to be 1,000 kilograms times 10 meters per second squared times 60 meters, minus the work done by friction. The work done by friction is the force of friction, which is 10 newtons, times the distance over which it acts is 150 meters. That's going to equal 1/2 1,000 kilograms times VB squared. That's your only unknown. You know all those other things, so it's solvable. Let's see if we can solve it. 1,000 times 1 is 1,000. This is going to be 500 joules. This is going to be 1,000 times 10. I made that a 1,000 kilogram cart. Let's make that a 100 kilogram cart, because that's what I wrote. Sorry about that. So this is 50 joules. So 50 joules plus 100 times 10 is 1,000 times, this is 6,000. So I have 6,000 joules, 6,050 joules of potential energy. But I lost some of it because friction did some on me, which is going to be 10 times 150, which is 1,500 joules of energy. That's lost, again, primarily into heat. It's not lost in the universe. And that's equal to 1/2 times 1,000 is 500 times VB squared. Now, if we do the math, I get 6,050 minus 15 is 4,550. Check the math. This would be 4,500 plus, that's it. So 4,550 joules is equal to 500 times VB squared. Divide both sides by 500. That's gone. 4,500 divided by 500 is going to be a little bit over 9. We got a calculator to do that. So we'll go 4,550 divided by 500. And I got 91. So VB squared is equal to 91. So VB is going to be the square root of that. So VB is equal to 3.1 meter per second. One that's a little drawn out because of the fact that you have it, but it accounts for everything. And that's a real world number. Now, you could always just go back to your original statement if you want and check and see what it would be without friction. It should be a higher number. Friction is going to decrease it as you do it, so that's kind of a way to check it. And again, I can do one of two things. I can subtract the work done by friction off the top side, or I could add the work done to friction on the other side. Mathematically, it makes no difference. They're exactly the same when you do it. So that's a more complicated problem. We'll play with this some in class, but realize, big thing you understand is work done by friction is equal to the lost energy. And that's kind of the crux once friction is involved. And in the real world, friction is involved. Hope this helped.